Going to discuss the topic heat transfer. See, under the topic of the heat transfer, how can be heat transferred from one place to other places in different procedures. First, you observe this. If you are taking the metal rod, if you are heating at this point here, of some time you will reach that particular heat can be transferred through this material. Next case, suppose if you are taking that vessel, in that vessel if you are taking that liquid, if you are heating this liquid at the bottom, after some time the heat can be transferred to the top. Third case, if you are standing in the sun daytime, of some time if you observe that your head will get particular heat getting transfer. So first case, what happens that heat can be transferred from this end to this end without movement of any mass particles. Whereas the second case, heat can be transferred from bottom to top by movement of these particles. Here mass transport occurs. Here without mass transport occurs. If you observe this third case, that is a radiation without medium, here there is no medium. Here the medium metal rod, here the medium is liquid here. Without medium, the heat can be transferred from sun to earth. So this is the process what we are calling as thermal conduction process. This is convection process, and third one is radiation process. So in the conduction process, the heat can be transferred from one point to other point without the mass transport. Whereas the convection, heat can be transferred from one point to other point with the mass transport. Here the water molecule or liquid molecule can move like this. Whereas the third one, under the process of radiation, there is no requirement of the medium, but heat can be transferred. Now I will introduce about the thermal conduction. Suppose this is the one hot body, like T1 temperature, and this is then another cold body here, T2 here. Here our assumption is T1 greater than T2. That's what our assumption. This particle A here, this particle B, this is that hot body, this is cold body here. The thermal conduction here, what happens that they should be directly contacted with some other metal rod. Here our assumption is this metal rod sidely insulated completely. Here the insulated and here also insulated. So definitely the heat can be transferred throughout this area of cross section. There is no loss of heat by means of the sides because sides are insulated. Here if you observe this, T1 greater than T2, the heat can be transferred, that can be with respect to time dt, is directly proportional to this metal rod area of the cross section is A here and length is L. This can be directly proportional to the area of the cross section and again is directly proportional to the temperature gradient dt by dx. If you are applying these two equations, dq by dt is directly proportional to A dt by dx. This can be dq by dt is equal Ka dt by dx. What do you mean by this constant K here? K is the coefficient of thermal conductivity of metal rod. This is the ability of this metal rod, how the heat can be transferred from this particular hot body to cold body here. We are writing this dt, the temperature difference. We are taking T1 minus T2. Our assumption is T1 is more than T2, and dx, this is how the heat transferred to this element. So I am taking that metal rod length is L. So definitely I am taking that L here. dq by dt is equal to Ka into T1 minus T2 by L here. So dq by dt is equal T1 minus T2 by L by Ka. This is dq by dt, this is the rate of heat flow. This can be equal to the temperature difference by some constant L by Ka. It is similar to our electrical analogy here. Let suppose this is the point A here, this is the point B. Let the potential difference is V here, let the resistance is R. We can write down current, electrical current I is equal to V by R here. See that this is about the delta V, that is the voltage differences. Here dq by dt, what we are writing, delta T by some constant. It is applicable to that this current, heat current, is directly analogy with electrical components. Here we are taking that potential difference, whereas the same analogy in the thermodynamics, we are taking this is about temperature difference. This is electrical resistance. This factor, what we are taking this is thermal resistance. So thermal resistance R we can write down directly L by Ka. L is the length of this rod, K is the coefficient of thermal conductivity of the metal rod, this A is the area of the cross section. If we are taking this R is equal to L by Ka, this is our new term, that is thermal resistance. There are the two metal rods are connected. This is our T1 and this is the T2. This is the hot body and this is the cold body. They are connected by these two metal rods. Let their lengths L1 and their lengths are L2. Our assumption is area of both the cases are same. Now we are going to discuss about what is the temperature formed at the junction of these two metal rods. Here this metal rod and this metal rod are connected in series combination. Now we are going to discuss, let the T1 is one end and T2 is the other end. Our assumption is T1 is greater than T2. What is the temperature is maintained at the junction by the heat flow. Let my assumption is T is maintained at the junction. So how can we write down by using this heat current, that is I is equal to dq by dt. We derive this. This can be temperature difference by thermal resistance L by Ka. So here from the heat current flows from higher temperature T1 to T first in the metal rod of L1. So thermal current I is equal to, what is the temperature difference, T1 minus T by, let its resistance is R1. This R1 is the thermal resistance that can be equal to L by Ka here. So in this case R1 is equal, its length is L1, its coefficient of thermal conductivity is K1 and area of the cross section is A. If we apply the same thing to the second metal rod, here the temperature is T here, here the current is T2, the current flows from higher temperature to lower temperature. Now comparing to this T and T2, it will be the more than this T2. Comparing to the T1 and T here, T1 is more than this T. So our current flows, heat current flows this direction. I am writing this second metal rod, I is equal T minus T2 by R2. If I are combining these two equations, T1 minus T is equal to I R1 and next T minus T2 is equal to I R2. If I are combining these two equations, T1 minus T2 is equal to I into R1 plus R2. So I is equal to T1 minus T2 by R1 plus R2. This is the current flows. Next, this is the T1 at this one end and T2 other end. R1 is the resistance of the metal rod, R2 is the next metal rod. So, total current flows through this T1 minus T2 by R1 plus R2. So, if you are applying this general equation, I is equal what is that? Delta T by R. So, here we are taking the two metal rods R1 and R2. Here R effective, in the place of R effective, we can write down R effective in the series combination is R1 plus R2. In the electricity, we are using two resistors R1 and R2. If they are connected, the series combination, effective in the series combination, there also we are taking R1 plus R2. In that heat transfer also, we are getting in the metal rod R effective is equal to R1 plus R2 in the series combination. Next, how can you find out that effective K value? So, in the series combination, R effective is equal to R1 plus R2. Now, we have that K1 is a one metal rod coefficient of conductivity, K2 is the second metal rod. We have to find out the effective of K value if they are connected, K1 and K2 are in series. Here, this is the metal rod and this is another metal rod. Here K1 and K2 here. This is L1 and L2. This is the area of the cross sections are same. This is the T1 and T2. We got that R effective in the series combination. Just now we derived R1 plus R2. So, we can write down this total L effective by R is equal to L by Ka. L effective by K effective into area of the cross section for all the cases are same. That is our assumption. R1 is equal L1 by K1 into A plus L2 by K2 into A. See all the cases L effective. So, here if they are taking the two metal rods, L effective will be equal to L1 plus L2. Suppose if you are taking the 3, L1 plus L2 plus L3. If you are taking n metal rods, L1 plus L2 plus L3 plus so and so Ln. Here I am taking the two metal rods. That's what L1 plus L2 by K effective into A here. If from here K A is a common, L1 by K1 plus L2 by K2. So, A gets cancelled. So, K effective is equal to L1 plus L2 by L1 by K1 plus L2 by K2. Let n metal rods are connected. If you are substituting the same formula here, L1 plus L2 and so on Ln by L1 by K1 plus L2 by K2 and so on Ln by Kn. So, this can be equal to sigma Li, I is equal to 1 to n, sigma Li by Ka, I is equal to 1 to n. This is about K effective in series combination. In the examination, generally we are expecting the questions, what is the effective of K R effective and what is that effective value of the K. Now, we are going to discuss some series combination problems. If you observe this, a steel frame of length is given and cross sectional 0.20 centimeters. It forms three sides of the square. The free ends are maintained at 20 degrees centigrade and 40 degrees centigrade. Find the rate of heat flow through the cross section of the frame. If you observe this, it is a square is maintained, but our given problem, what happens is it forms the three sides of the square. One is, let this is L here, this is L here, this is L here. These are the maintained as a free ends. The free ends are maintained at 20 degrees centigrade and 40 degrees centigrade. Here the given problem, what happens is that the particular frame of total length is maintained at three sides of the square, means the total length of between these two sides, this side and this side, this and this one, all the same lengths. Here he is asking that find the rate of heat flow through the cross section of the frame. Just now our derivation based on let this maintained at T1 and T2, let T1 is greater than T2, how the heat flow from higher point of the temperature to the lower point of the temperature. Here the free ends, one free end is maintained at the 40 degrees centigrade, one is maintained at the 20 degrees centigrade. Definitely heat flow, it moves like this. He is asking that rate of heat flow, how can we take this rate of heat flow is nothing but heat current, dq by dt is equal Ka dt by dx. Here K value is given in that question, K is equal some 45 here, area of the cross section is given, that is 0.20 centimeter square. So you have to convert into a SI unit. And dt, temperature difference. So what is the temperature difference here? 40 minus 20 by dx total length change. See here, this from here to here L, here to here L, here to L 3L. Our given total length 3L is equal 60. So total length you substitute. This way you will find out that rate of heat flow. Next we are going to discuss another question.